Another draft physics video presentation. Franklin who? Okay, the science chat Saturday thing, and 2 hours. And so Franklin mostly presented his, again, theory of a photon, and we didn't advance the conversation much in terms of whatever video exchanges we've made so far, but I will poke at this a little further. So as it says, he says shape of a photon is a rod. So he's kind of arguing that a photon is traveling through space like a object, like a pen, that has a length that's longer than its width, and I guess it has, no real depth, not any more significant than its width, something like that. And that somehow this hits and it says 500 nanometers. Or it says 350 nanometers or something. Something like that. Now, I don't know, he didn't really talk about the fact that the polarization increases or decreases, that is the length, with the frequency. And he didn't say anything much about that. Now, he did paraphrase my theory as being, I'm calling a photon a clump. And clearly, that's not a very good paraphrase, frankly. I'm saying no, it's a pattern in space. So the first argument I would make is that, the difference between what we're arguing, him and I, all right, is there's these basic things that a photon has, all right, and one of them is frequency, all right, and that's, it's a really important thing. Can't quite see his little rod theory here. Make it a little round one. So there we go. All right, so I'm saying the polarization just has to do with some separation in the parallel path of bullets. And that would be the polarization. And that would be proportional to the wavelength, pretty close to the same thing, sort of equal. And that there's a certain number of component bits that have to hit a surface for it to be received as a photon. So a photon is a composite object made of pieces of momentum and events. Without events, there is no photon. So I really don't understand how he says this flies through space, it hits a surface, and somehow the surface knows that's 500 nanometer, light. How does it know that? I mean, how does this tell this what frequency the light is? There's no. How does it know? It's like getting hit with a baseball and somehow you know something more than the fact that the baseball has a mass and a surface. You don't really know how thick the baseball is, right? You're not measuring the thickness of the baseball. How do you measure, something like frequency out of something that just hits? So that's just to clarify. That's the contrast between the theories. All right. So I don't know what more there is to argue. I'm saying that a photon is a pattern that hits a surface. The pattern has to hit, like adding energy to a pendulum. It has to hit, and then it has to wait for the swing or whatever, and then hits it again, and then it hits again. I mean, technically it has to hit before the electron can move back to its position, and then it has to hit it again before that happens, and that's energy. That's why an electron gets kicked out of an atom. That's the photoelectric effect, is hitting electrons that are on the move before they move back. And therefore, then you can move them to a new position that's further away from the proton, and therefore it can be sucked away, so to speak. It can leave the atom. It can cause ionization. So ionization energy is essentially what you're talking about. How much energy it takes to ionize, and it takes the energy in the right sequence. If you add the energy in the wrong sequence, just like with a pendulum swinging, if I poke it when the pendulum's swinging against me, I'm going to take energy out of the system. I'm not going to add energy to the system. And the argument's that kind of simple. That's why it's all frequency dependent. higher frequency implies more energy. I mean, obviously, the closer together the bits are, the more energy fits in a space. But that's really the only relationship that exists. The little bits, the bullets, always have the same amount of energy, and it's just how many bullets in a certain amount of time is going to dictate how much energy, total energy. But we're really just talking about what electrons are sensitive to, and that's why every substance is sensitive to different colors of light and different frequencies of light. Because it's not about the energy, it's about hitting it at the frequency at which it resonates. The atom resonates, like microwaves and water molecules. They obviously have a relationship that the microwaves happen to be at a right frequency to add energy easily to water molecules. All right. So the other stuff, I'll just go through some of what we know from experiments, and yeah. So, well, I guess I could clear this. All right. To just be clear, so although Franklin says the photon is this cylinder thing, this rod, you know. It's kind of funny listening to the video, men talking about their rods. This cylinder, this rod moving through space, he really says it's made out of a wave. So it's a wave that looks like a rod, I guess. Which again is, to me, incoherent. But whatever. Waves and shapes. But anyway. All right, so one of the things that, I have sort of played with, and not been very explicit about, and like I said, I sort of knew better, was polarizing filters. So we have this impression that, you have two antennas, say this way, for radio waves, and that if you put a filter in between going the same way, that the waves go back and forth freely, and it doesn't block the signal. And the catch is, though, that's not true. The filter actually is this way. Okay, that's the filter that lets the radio signal through. Is the one opposite, perpendicular to the shape of the antenna. So, and you can see this, especially in the radar experiments. I mean, I haven't seen it myself, but yet they tell you in every one of them, okay, the antenna is going this way. They put the filter in this way, and the signal gets through. So, the polarization and the filter are opposite each other. So, the idea of sending the rod of energy through the bars of the filter isn't going to work, because that's not what the evidence demonstrates how most of these filters work. Now, it's true that the light filter could be doing something different, and I'd argue I think it is, but I don't think it's completely different. Okay, so but it's worth bringing up that it seems to be, it shows two things that to me demonstrate that you have to think of photons as composite objects. As something you can break and then you remake. But you could understand the polarizing filter is just, as I've sort of described, there's nothing blocking any light. There's nothing absorbing light. The filters would get hot if they did do that. And what it's really doing is setting up a layer and then having a second layer on top of that layer that just changes the polarization. So what you're really doing is you're having a 1x change in the polarization, and then where there's a second layer, it's 2x. And so it's 2x and 2x. So you could understand that it's filtering that way by retarding the light's progress, that is, creating places where the light slowed down more and places where it slowed down less, that you would knock the light out of phase, and that could be an explanation. But regardless, what the filters really demonstrate is that you can put a quarter filter in and defeat the blocking of the 50% filters. So there's a 50-50 here, and it would be 100% blocked, but if you put this filter in, you get whatever, 25% is recovered. So you know, that's sort of demonstrating that you can't recreate photons here. So whatever was in this space, okay, has to have, okay, photons. So you're still going to lose the ones here, right? You're going to lose 50% here. So you have to somehow recover some of the 50% you lost here with this filter to be able to overcome this 50% filters that's going to hurt you. So you have to be doing something to whatever's in here, and there has to be enough in here for you to overcome what that 50% filter is going to do. And so I think the only logical choice is to understand that, well, all you did is you broke photons, and then you can fix them again. So you can break their polarization, you can put them out of phase. You know, take a photon that's this, and you can break it and have the phase doing this instead. And then you can remake it by readjusting these photons, you know, these other two on the end. You can put the phase back and put it back in alignment in terms of the right phase. And that would be a more reasonable explanation for the effect. But, you know, we sort of have to be clear about some things. I guess we have to establish the premise for the argument. And I guess, you know, at one point in the video, he states that he thinks radio is entirely different than light. And I would argue that it's all just, the only difference is the size of the antenna, you know, and all you're doing is saying, you know, light's just a very small antenna, you know, versus the radio waves. And that's all. It's just an antenna size, and light is created in the same way as an antenna, and the polarization sort of demonstrates that, because the polarization is 1,000 atoms of height. So how does he propose those 1,000 atoms create the effect when everybody's arguing that a single electron is creating a photon? And I would argue, no, a single electron can only create part of a photon. It can't create a whole photon. It can't create the whole pattern. It can only contribute a piece to the pattern. So something else I'd say about antennas is that the process, the reason antennas are a certain size, and there's certain advantages to those sizes, is that if you think about the antenna's length, okay, versus at the speed of light, how fast electricity can travel up the antenna, and then talk about the frequency of the radiation you're pumping into the antenna, you can sort of figure out that there's a certain amount of distance at the speed of light electricity can travel at, say, 2.4 gigahertz, right? So 2.4 gigahertz would equal about 12 centimeters of distance. And, you know, between the frequency bits. So there'd be 12 centimeters of distance between the bits, where 500 nanometer light would be, you know, much smaller than that, you know, a few 100 billion times smaller. But anyway, so you can think of the antenna, the ideal length would be that's 7 inches, let's just say, for Americans. I guess it's more like 6 inches, but whatever. It's more like 5 inches, I guess. All right. So, but what happens when you start going longer than that is the argument is that your signal is a pulse, it's saying something, and as it's pulsing, it's starting in down here at the first point, and that's saying, you know, signal on. And then it says on going all the way up, and you can sort of understand that by the time it says on here, this on, the first on at the bottom of the electric current, that one is already now at its frequency mark. It's traveled the 7 inches, you know, 5, we agree. It's traveled the 5 inches through space by the time this one says on. Okay, so the signal is sort of coming out this way. So you can sort of see that a second signal is now going to be out of phase with that first signal. So if it starts saying on in this later phase, that's going to be putting another signal on top of this signal that's out of phase with this signal. So in a sense, this signal is going to be competing. You know, the signal created by this antenna, okay, is going to end up competing with the signal sent by this one. In terms of the phases are going to be, you know, a half wavelength or whatever out of phase. So that's why the extra antenna doesn't do you any good. It can only do you harm. You know, to have an antenna longer than the usable part of the antenna, you end up just creating a second signal that'll be out of phase with your first signal. Now, I guess I would argue that the ideal antenna would be half this length. And I heard something about that somewhere, because that would guarantee you don't get half. That would guarantee you don't get the signal being a full half wavelength competing with the original signal. So anyway, the signal is traveling through space essentially with that angle in it, and that's what I'm arguing is, you know, commensurate to the polarization is this. You know, you can make a square out of it and just say, yes, the frequency and the polarization will end up being the same thing. All right, similar, proportional. So, so the same thing's happening in light, but, you know, as you can make this antenna shorter and shorter, the amount of difference in time gets less and less and all that kind of crap. But it's still the speed of light. So it's the speed of light for the electricity to travel through a material, that is the atoms to move, and it's the speed of light, you know, that the bits have to fly out. And we're really just talking though about electrons flying out. All right, so yeah, before we can, you know, you can't go too far until we get this part settled. So the first argument is that polarization is really big, okay, 1,000 atoms, that we can't receive light unless it is polarized. That's sort of been demonstrated. We can't send any form of energy through both polarizing filters. Okay, we can't send any form of light through both filters and have it show up over here. So we can't take away its polarization. Somehow we can't make light perfectly, you know, no atoms high, just pulses at a dead straight line. Somehow we can't make a photon that doesn't have thisness to it, this part of the height. Because if we could, then we could just shoot it through a filter and land it on a tinier location, and we just can't. There's no evidence that's ever been done, none that I've ever seen. So polarization is part of how a photon arrives on a surface, and I would argue that it matters when the bits of energy hit. And so just how that radio wave is shaped, it matters that one bit hits, and then the energy hits again, and then the energy hits again, because it's essentially trying to push something in a direction. And so it rolls the ball a little bit, and then it hits again to push it further, and then maybe it hits it a third time to push it further. So it's accelerating an electron. It's not accelerating necessarily the same electron, right? Because this is atoms of material. So you're saying you're hitting an atom in a location, giving the electron energy. Let's just convert the energy into this direction. That travels through a couple of atoms, and because the timing is right, because the light was created the same way it's landing, and it's going to be frequency dependent, this time will be the same as the time difference between when it was released. And so this one shows up just in time where this ball is here, the electron is being switched, and it adds more energy right then, and it gives the electron a boost. So the electron is already moving fast, flipping between the atoms, and then it gets moving faster because it gets a second hit, and then maybe it even gets a third hit. And that's what makes the difference between something we call a photon and something that out of phase or the wrong frequency, and the light hits here instead of here, and obviously it can't push it because it's too late. right? The arrow hit here too late, and or too early. Well, too late in this case. Wait, narrower polarization would be higher frequency. Yeah, so that would be proportional to the fact that this is where the energy would be if it was. But if I tried to stretch red light and make it a wider polarization, you could see then it would be hitting here. And if I made the red light too narrow polarization, then it would be hitting here when the energy was here. So that would not work either. So the polarization is just as important. Polarization is about how light is realized, or how it's converted into electricity. It isn't converted into electricity unless it does come at a sequence. Unless it does have to hit the surface across an area of the surface. If it hits the surface all in one place, it won't do anything. It does have to hit progressively. Yeah, that's probably the way I wanted to say it. Anything else? So I still argue the underlying theory. He believes the universe is made out of a bunch of big giant, whatever, positrons and electrons. And I would argue that no, there's no ether. But there is a big sea of little bits of energy in the universe. And every time an electron moves quickly, it collects all the energy between the point A and the point B. It collects all that energy and compresses it into a much smaller reflection. So the space of the energy between me and this piece of, between the camera and this piece of chalk, there's a whole hunk of space. I'm arguing that in that space right now is a whole bunch of little pieces of this force bits, these little bits. Some of them are photons, actually. And what I'm going to do by moving this quickly is collect all of them, in the sense I'm going to reflect all of them. And if this is moving really fast, half the speed of light, it's going to reduce the amount of space that all those bits were in half. I'm going to take a circumstance where there was a certain density of stuff, okay, sand, whatever you want to call it. So let's just say it was grains of sand and they had a certain density. But they're moving. Well, it just doesn't really matter. And I take something solid and I push it into them. You can sort of understand that each one of these reflections will happen at these points. But each one of these points now is going to be the speed of light. So let's say if it was going the speed of light, you can understand that this reflection will happen here at the speed of light. Well, this one will also happen to be exactly the same reflection time as this now, because I moved this distance at the speed of light, which was the same speed as this one was going. So I moved the same speed as this reflection, got to another point, hit another thing, and now I'm adding another reflection that's exactly in line with that one. And when I hit the next one, I'm going to get there at the speed of light. So all of these arrowheads will be in the same place. Arrowhead, arrowhead, arrowhead. Now I'm going to add another arrowhead. And when I get to another bit, I'll add another arrowhead. So at the speed of light, I'll convert it all the energy, all the grains of sand here. I'll make them all, okay, be reflecting off the surface now. You know, at the same point, especially if I stop it instantaneously. If I stop it, all of that stuff would just keep going at the speed of light. So I took everything that was in this big giant piece of space and I put it into this little tiny piece of space. And that's what electrons are doing. They're pushing energy, force. They're reflecting it. And by reflecting it quickly, they're taking something that was rarefied and they're compressing it. You know, but it's not an ether. Alright. So we'll leave it short just to get those couple of subjects out of the way and see if there's any ground for any kind of communication. I mean, it's disappointing. We only had a couple hours worth of exchanges and advanced the subject nowhere in terms of establishing what I would argue that, you know, his theory is wrong and each element of it is wrong. And the only thing right about it is, you know, at least he is recognizing that polarization is a real physical thing. It exists in space. and that this stuff isn't made out of stupid, magnetic fields and electric fields. It's not made out of made-up mush. It's made out of something real. But his shape of the photon doesn't, in my opinion, include the most important part of the shape, which is its frequency. Alright. Something like that. So, and I certainly don't go for this ether made out of matter thing. Just, how do you move all that matter around? It just doesn't make any sense. It takes energy to move matter. Matter consumes energy. And if space was made out of matter, then nothing would ever happen because everything would grind to a halt very fast. Alright, enough of a video. Until next time, as such.